In this example problem, we're going to look at a problem that involves relatively complicated motion of three particles tied together, all in motion at once. We're going to first examine it using conservation of energy. So that's our first approach to solving this problem, and we'll talk about when that's appropriate. And then in the second part of this problem, we're going to look at the forces and torques approach to solving the problem. So let's take a look at the system. The first thing we need to understand is the dynamic of each of the pieces of the system. So the first object we're looking at is the M1 particle. So we're considering that to be a solid uniform disk, and you want to think of it as like a yo-yo, where there's going to be a string attached to the central axle in a way that we don't care about the mechanics dynamics of it, that allows this wheel and axle to spin freely such that the tension in the string, again, will act like a rolling pin, kind of pulling it to the right. Now, that string is then going around the pulley. So the pulley is, again, also a solid cylinder. And then the string attaches to the mass M3. And when M3 falls down, this distance h, it spins the pulley. And it translates and rolls the wheel along. So the wheel is going to translate and rotate. The pulley is just going to spin, and the mass is just going to fall. Please notice, when we do this solution, we don't use the energy solution. We don't use forces at all. On page 14, this entire page of notes, we do not mention forces. It is strictly an energy approach. It is very important for you to know that static friction, that friction that absolutely is necessary for the mass M1, right, to roll without slipping. So the static friction between the base of M1 and the ground, which if it weren't there, the wheel wouldn't roll. It would just skid. It would just move to the right without rolling. But that static friction does not generate heat or reduce the energy of the system, so we can still use full conservation of energy, meaning the kinetic initial in the system plus the potential initial in the system equals the kinetic final plus the potential final. And as always, when we solve our problems using conservation of energy, if we can get our zeros in there, we do that. So that's why we note that the system, we are told, starts from rest. And the only potential energy in this problem comes from the mass M3, which is going to fall down a height h. So it's going to lose potential energy. The system's going to gain kinetic energy. So the initial potential energy is just our M3GH. And then we have to take into account every single piece of kinetic energy in the problem. And that means M1 has both translational kinetic energy and rotational kinetic energy. The spinning disk only has rotational kinetic energy. And, of course, the mass M3 will get just translational kinetic energy. So all of that kinetic energy has to be taken into account. Okay, so note that the string in this case locks the system together. And, again, I have it highlighted here. I ask you to please get this into your notes and highlight it, that the string ties this system together figuratively, literally, mathematically. All of the V's in this problem are going to be the same. Now, V center of mass equals omega r for M1 is not a result of the string. That's a result of the no slipping. But then everything is the string. So the tangential velocity on the rim of M2, so the tangential velocities out here will match the linear velocity of M1, and the rotational tangential velocity on the rim of M1, as well as the linear speed of M3. So as I've stated here, we can drop the subscripts on all of the V's, and we do. So let's drop all of the subscripts on all the V's, and when we go from our kinetic energy just general statement to our specific kinetic energy equation, all of the V's just become V's, no subscripts. So let's do it. We have our M1 V1 center of mass. We drop the subscript, 1/2 M1 V squared. Now we have 1/2 I1 omega 1 squared. Well, I1, moment of inertia, 1/2 mr squared for a disk. And V equals omega r, so omega equals V on r. So I have to keep the subscript on the R1 because the disk 1 is smaller than disk 2. So disk 1 is 0.1 meters, disk 2 is 0.02 meters. So we have to keep the subscript on the R, and then we just keep going along. So we have the moment of inertia of disk 2, 1/2 m2 r2 squared. The omega is V on r. The subscript is off of the V. We leave the subscript on the radius 2. And then we have the kinetic energy of the falling mass. So you can see we get some nice cancellations here. We lose the r1 squared. We lose the r2 squared. So what we are left with is just 3/4 m1 v squared, 1/4 m2 v squared, 1/2 m3 v squared. And now it's just algebra. So we plug in all of our numbers, and we get that the speed of the system is 1.68 meters per second. And again, that is the speed of the entire system. It's the tangential speed on the rim of the wheel. It's the linear speed of M1. It's the tangential speed on the rim of M1. It's the linear speed of M3. And let me erase here for 1 second so you have a clean page to look at if you want to pause the video. Please make sure you get all of these annotations down into your notes. And just to emphasize again, notice there no forces were listed on this page. It is purely an energy calculation where you don't have to get all involved in multiple equations and multiple unknowns to solve to get the speed of the system. We're now also going to look at breaking it down into forces in our next lesson.